Suppose you have a car driving down a road, moving in one dimension. The equations of kinematics handle the case where there's a constant acceleration. The car is smoothly going faster and faster, or slower and slower. Now, in order to define these properly, we have to, as usual, choose where 0 is and which way is positive. So if we take the starting position of the car as location 0, and say that's the positive x-axis and measure along that way, then we can use these formulas to describe where it will be, how fast it will be going at any given time. So far, so good. It turns out these formulas are a little more robust than just going in a straight line, because if you had a car going along a winding road, bird's eye view, you could still use these formulas. Now, they won't be the whole story because they're not describing the zigzag, but if you were to put your origin here and to curve your positive x-axis, then these equations will still apply to your motion along the road. This is what's called tangential motion. So we could talk about the tangential distance along the road, the tangential velocity, the tangential acceleration, which is measuring how much you're speeding up or slowing down. These exact same equations would hold just fine on a winding road, provided you don't think about the sideways motion or deal with it separately. All right, so we have the idea of tangential motion. Let's go to a more specific and more interesting case. What if we are driving around a circle? So if the car is here and heading that way, we can measure the positive x tangentially along this road. But there's another thing we can measure here. We could also talk about the angle. We could describe how far this car has gone in terms of the angle that it cuts across or subtends with the center of this circle that this road makes. So the car's initial position and final position subtend an angle from the center of the circle. What's the relationship between the angle and the tangential distance along the road? Well, it's clear that it's proportional, because if you have twice as much angle, you're going to have twice as much distance. But what's the constant of proportionality? Let's take a little detour into circle geometry, and we can figure this out. Now, even if you don't already know the formula, you can reason it out, because you can say, well, if I've got theta degrees here, and I don't know the formula for how long an arc is, there is one arc I do know. I know the circumference of a circle. I know the distance all the way around. The circumference is 2 pi r. So if I've got x, that's going to be a fraction of 2 pi r. What fraction? Well, theta degrees out of 360 degrees times 2 pi r. That would give us the tangential distance. All right, great. We've got a relationship between x and angle. However, this is messy. I want to use this formula to derive a whole bunch of other formulas, and I'd really rather not have 2 pi over 360 degrees hanging out in every single one of them. Is there any way we could get rid of that? Well, degrees, why are they there? The degrees are arbitrary. It was like Babylonian or something. 360 ways to cut a circle. That was just a historical accident that somebody set up that scale. We could make a new scale. In fact, we could make a new scale that we could call radians. Theta radians is theta degrees over 360 degrees times 2 pi, which means we get the nice tidy little formula x equals r theta, provided theta is in radians. So that's important. You may have seen it in a geometry class many years ago, but there it is, derived. I thought that would make more sense. So this is our starting point, x equals r theta. What can we do with that? Well, we can start with x initial equals r times theta initial. X final equals r times theta final. We could subtract them and say x final minus x initial equals r times theta final minus theta initial. And we could call that delta x equals r delta theta. No big surprise there. But now here's the surprise. Let's divide by time. Now what are we talking about? Delta x over delta t is velocity. In particular, the tangential velocity as we go along the road. So we have tangential velocity here, and it turns out to be r times this thing. This is radians divided by seconds, so it's measured in radians per second. You might hear it in more familiar units of RPM, revolutions per minute. It's how fast something is spinning. It's actually called the angular speed or angular velocity, and its symbol is small omega, right? Like that's a big omega, that's a small omega. It's not a W, it's an omega. So V tangential equals R times omega. Depending on how fast an object is spinning, you can tell how fast a point on the rim of the wheel, say, was moving. And if you have a car driving around a curve, you could figure out how quickly the angle is changing based on how fast the car is moving. They're proportional with radius r. Since that was such a great trick, let's do it again. V initial equals r omega initial. V final equals r omega final. Delta V is therefore r times delta omega. And let's divide by time again. If we do that, the rate of change of velocity, that's tangential acceleration. That's your acceleration along the curve, not centripetal, tangential. That's the number that says how quickly you're going faster and faster and faster, or slower and slower. What does it equal? Well, we need a name for this too. If we're talking about angular acceleration, we should call it something like alpha. Here we have our key formulas. X equals r theta, V equals r omega, and A equals r alpha. These are tangential, distance, velocity, and acceleration. So let me point out some things about the units here. X is in meters. V is in meters per second. A is in meters per second squared. That's familiar. R is in meters, which means theta should be in blank. The radian is what we call a dimensionless unit. But how could you have a unit without a dimension? Well, how about dozen? It just means 12, but it's not 12 inches, not 12 seconds, not 12 kilograms. It's just 12. Avogadro's number, 6.022 times 10 to the 23rd. It's just a big number, but it's a unit for counting things. You can count things by the dozen. You can count them by the gross, or the score, or the ream, or whatever other large things you care to use. Radian is a dimensionless unit. And I call it the amazing appearing, disappearing unit. Because if this is in radians, a meter times a radian is just meter. Poof, radians are gone. Likewise here, if you have meters times radians per second, you end up with meters per second. And likewise, alpha here is in radians per second squared, and r is in meters. And when you multiply them, the radians vanish and you get meters per second squared. What's even funnier is when we go the other way. If you have x and divide by r, you have meters, and you divide by meters, and you get theta, and poof, appearing out of nowhere, we have the unit radians. So one thing you have to watch out for is when you're doing these formulas and you have meters over meters vanishing, you will end up with radians. And likewise, you could end up with, blank over seconds, and that means radians per second. Blank over second squared means radians per second squared.